Hi, my name is Serene Hassan. This project is about detecting IoT attacks with data analysis and machine learning. IoT devices are everywhere homes, offices, industries. This makes securing them very critical. Coming from a cybersecurity background, I approach this dataset like an SOC analyst, looking for what the data reveals and how the models can help triage threats faster. Let's start with the problem here. IoT devices generate massive traffic, which makes real-time detection challenging for SOC teams. The goal? It's straightforward, to triage IoT traffic quickly and effectively. To do that, I worked with a Kaggle dataset of about 10,800 logs across 5 attack types, which makes it reliable enough for model training. It also contains 17 lightweight telemetry features, things like timing, packet ratios, and durations. No deep packet inspection is required, which makes it practical for real SOC deployments. Here's the pipeline I followed for this project. I started with cleaning the data, where I removed IDs, handled missing values, and normalized features. Next came the EDA, where I explored attack frequencies, correlations, and standout features. From there, I moved into modeling, testing logistic regression versus random forest. Finally, I wrapped up with insights. Using feature importance scores and confusion matrices, I was able to identify what the models were relying on most and how their predictions could be improved. This takes us from raw IoT traffic logs all the way to SOC-ready insights. Here, we're looking at the distribution of labeled attack types in the dataset. The first thing to notice is that the dataset is fairly well balanced across the 5 categories, each around 18 to 22%. Most of the samples are focused on denial of service, man in the middle, and reconnaissance traffic, along with normal benign traffic. These represent the more common IoT scenarios. From an SOC perspective, this balance is good because it means the model isn't just memorizing one dominant class, it's being trained to recognize a spread of different behaviors. This is the correlation heat map. We can see here that there's a lot of redundancy. For example, some packet ratios and duration ratios are almost duplicates. We also see ID fields like source, destination, and second. These act like shortcuts but hurt generalization. So why does this all matter? Because trimming redundant proxies leads to a simpler, cleaner model, while focusing on true behavioral features like ratios and durations helps with real-world SOC conditions. One of the most interesting features in this dataset is called the second. From the box plot, you can see it shows the widest variance across attack types and separates classes clearly, but it behaves like an ID, excellent in this dataset, yet risky for unseen traffic. So while it's powerful, SOC analysts should treat it cautiously, almost like a crutch the model can lean on, but one that may not always be available in the real world. Here, I show how I prepared the data for modeling. First, I split the data 80-20 with stratification so each class was fairly represented. I then trained 2 baseline, logistic regression, a simple linear model, and random forest, a nonlinear ensemble with 300 trees. This contrast allows us to see how well different approaches handle the problem of IoT attack detection. And here are the results. On the left, you see results from logistic regression, and on the right, from random forest. From now on, I'll call this LR. LR accuracy is only about 35%. This tells us that linear models really struggle here. It underfits and fails to capture the complex relationship in IoT traffic data. With regards to RF, accuracy jumps up to 70%. That's double the performance of logistics regression. The result confirms that IoT attack detection requires more flexible, nonlinear methods. Random forest becomes our best baseline, setting the stage for further improvements down the line. One of the advantages of random forest is that it highlights what drives predictions. Here, the top signals are detection, source, and second. We also see strong contributions from ratios and durations reflecting abnormal traffic behavior. So the model uses both IDs, this shows who's talking, and behavior patterns. That shows how they're talking. That's exactly what a human SOC analyst looks for. To test reliance on IDs, I reran random forests without them. Accuracy dropped to 57%, which is a modest decline. This shows that the model isn't just memorizing IDs. It's learning behavioral patterns like ratios and timings. The strength is important because in the real world, attackers often spoof IDs or cycle through them. And a model that generalizes based on behavior rather than static identifiers is much more resilient in detecting threats. So summarizing the key SOC lessons and takeaways, from the data and feature side, we've learned that balanced data sets help coverage, some redundant proxies should be trimmed, and second is useful but acts like an ID. On the modeling side, we've learned that random forest outperforms logistic regression, and ratios and durations are the strongest, most generalizable signals. The bottom line, we do not need heavyweight tools or deep packet inspection to spot these threats. With lightweight telemetry, we can build models that are practical for real SOC deployment. They're fast, scalable, and effective at triaging IoT traffic. And as a final visual, here's a consolidated dashboard view of the key charts. Altogether, this dashboard gives a snapshot of the end-to-end journey, the data set, the correlations, the baseline models, and the key features that drove the predictions. From an SOC perspective, it shows how telemetry can be turned into practical signals for threat detection. And with that, I come to the end of my presentation. Thank you so much for taking the time to carefully listen and understand. This project was my first real dive into applying data science techniques from the perspective of a cybersecurity analyst. My goal was to show how even basic models, when built carefully on balanced data and right features, they can uncover meaningful insights for SOC teams. Thank you again, and I look forward to applying this work in real-world security contexts.